Hello, this section is 15.3 on path independence, conservative fields, and potential functions. Now, as discussed in section 15.2, if the flow, or well, we talked about the work. If the work over some field from point A to point B taken through any path, it is the same along all the different paths. That means that the field is a conservative field. It is path independent. That's the definition. So first concept states, let F be a vector field defined on an open region in space, and suppose that for any 2 points A and B, the line integral that we talked about, the work integral or flow integral along a path C from A to B is the same over all paths. Then, if that is the case, the integral is path independent and the field is conservative. Okay? Now, another definition. If we have F to be a vector field, then we should be able to find what is called a potential function for F, okay, which is basically a gradient function. Okay, so the gradient, you know how to find it from the previous sections, and if that is the case, we have another definition here that states, let C be a smooth curve joining point A to the point B in the plane and parameterized by r sub t. If let F be a differential of a function with continuous gradient vector, F equals to the gradient of F containing C. Then, if that is the case, if we can find a potential function for F, then we can, instead of doing the line integral, we can evaluate it directly, f of b minus f of a, through its potential function. Okay, that will be the same as the work integral. I'm going to show you how to find potential functions in this section. That's going to be one thing that we will be working on. So that you know that when we do the potential function and evaluate it from point A to point B, or if we do the work integral from A to B, that will be exactly the same result. Alright. Now, let F be some vector field, and we talked about this in the previous section. M is the x, basically the x component, we call it M of your field, plus nj, the n being the y component of the field, plus pk. Okay, be a vector field whose components are continuous. So all of these components are continuous through an open connected region. Then F is conservative if and only if F is a gradient field, what's called the gradient of F for a differentiable function F. Let's go through these definitions and apply them to the problems in just a bit. And last, this is how we test if a field is a conservative field. And again, what does it mean by conservative field? That the work along any path is always the same, no matter what path we take. Then, given three continuous component functions, m, n, and p, for the I, j, and k components of a vector field, then a field is conservative. This field is going to be called conservative, which means that the work will be the same over all paths if and only if the derivative of the k component with respect to y is the same as the derivative of the n component with respect to z. Also, the derivative of the m component with respect to z equals to the derivative of the k component with respect to x. And last, if the derivative of the n component of the j component with respect to x is the same as the derivative of the I component with respect to y. These are the three tests that we have to fulfill in order for us to determine if a field is conservative, which means that the work over all paths is the same. Let's analyze a couple of questions, and I'm going to put the test right here on the side so that you know what is it that we have to do. And let's begin with the work. Identify the fields below as conservative or non-conservative. Okay? First test, we need to get the derivative of the k component with respect to y. Okay? The derivative of p with respect to y is equal to 2. Okay? Now get the derivative of n, which is the j component, with respect to z. The derivative of n with respect to z, right here, the derivative of this with respect to the letter z is also 2. So you see that they are the same. First part of the test is fulfilled. Second, the derivative of the I component with respect to z, that's what we're going to do. So this with respect to z would be 9, the derivative. Now that has to be the same as the derivative of the k component with respect to x. Now the derivative of this with respect to x will be 9. So you see, it is the same. Now we're going to get the derivative of the j component with respect to x. The derivative of the j component with respect to x is 9. And then that has to be the same as the derivative of the I component with respect to y. The derivative of this component with respect to y, it's also a 9. So, since all of these tests are fulfilled, that they are the same, that means that f is a conservative field. And by conservative field means that if I get the work from any point A to any point B, and I take any path, parabolic path, linear path, circular path, it doesn't matter which path I select as long as it goes from A to B, the work that is used to get from A to B, it's going to be the same along all the paths taken. All right, next question. Determine if this field is conservative or non-conservative. Okay, so we're going to do the same thing to determine if it's or if it's not. These are the tests, again, so we can keep them in mind. We're going to get the derivative of p, which is the k component, with respect to y. Derivative of the k component with respect to y, right here, is negative 10. And then we're going to get the derivative of the j component with respect to z. The derivative right here with respect to z would be 1 times 10, which is 10. What can we see automatically right here? That these two are not equal, right? Since they are not equal, we can stop and we can say automatically that f is not a conservative field. There is no point of continuing. That means that if I calculate the work from some point A to some point B along different paths, the results will not necessarily be the same. They could, but not necessarily. All right. Next. Now we're going to be finding a potential function. Okay? Now, in order for us to know that we can find a potential function, in the first place, we need to know whether this field is conservative or if it's not conservative. Now, in this case, if we're finding a potential function, we're assuming that these fields are conservative. If you're not sure, you can always verify that they actually are conservative. Okay? Just to verify that they are conservative, all we have to do is get the derivatives. Now, the derivative of the p with respect to y right here would be 3. The derivative of n with respect to z right here will also be 3. So they are the same. Now, check on this one. the derivative of the I component with respect to z right here, it's going to be 4. The derivative of the k component with respect to x right here is also going to be 4. So we get the same thing. See? Now right here, the derivative of the n component, which is the k component with respect to x, is going to be 3. And the derivative of the I component with respect to y right here is also going to be 3. Since it is the same, so all 3 tests are satisfied, that means that f is conservative. And according to one of the definitions spoken, since f is a conservative field, that means that f is equal to the gradient of some potential function f. Okay, what does that mean? What does it mean by gradient? Okay, by gradient we mean that this could represent the derivative with respect to x of some potential function. This represents the derivative with respect to y of some potential function. And this represents the derivative with respect to z of some potential function. That's how we determine or how we find the gradient of a function. So that's what follows. Then the derivative of f with respect to x, the derivative of some potential function f with respect to x is represented by this value, 3y plus 4z. The derivative with respect to the derivative of f, of some potential function f, with respect to y is equal to this value. And last but not least, the derivative of some potential function f with respect to z equals to this value here, which is 4x plus 3y. So then, we're going to find that potential function f by integrating. Okay, this is like an initial value problem. So we're going to be integrating it. So first I'm going to leave the df by itself. df equals to 3y plus 4z times dx. So then I'm going to integrate both sides. And we're doing the integration with respect to x right here. So we integrated with respect to x, that's going to tell us that the function f, okay, with respect to x, y, and z equals to 3xy plus 4xz. And according to the properties of indefinite integrals, that's going to be plus, it could be, since this is a function of 3 variables, okay, and we're integrating with respect to x, this last value is not necessarily a constant. It could be that that value that we obtain right here, it is a function. I'm going to call it some function g. Since we're integrating with respect to x and evaluating the x values of the function, then that possible function is going to be a function with respect to y and z. It could be. I'm not saying that it's going to be a function with respect in terms of y and z, but it could be a function in terms of y and z. It could be that it is just a function of y, it could be that it is just a function of z, or it could be that it is a function of both, or even it could be that it is just a constant c. Okay? That's what we're going to determine using these 2 other conditions. So now we're going to use the second condition. But for that second condition, I need to get the derivative of this function, but now with respect to y. Okay? Let's do that. So the derivative of this function with respect to y equals the derivative of 3xy with respect to y is 3x. The derivative of 4xz with respect to y is 0, right? And then plus the derivative of this function g with respect to y would be dg with respect to y. But guess what? we already know what df with respect to y equals to. This is equal to 3x plus 3z. That's our condition here. So I'm going to replace this value. I'm going to replace it here. And so we're going to have the following. 3x plus 3z equals to 3x plus the derivative of the function g with respect to y. Then if I want to solve for this, then we're going to have that 3z is equal to the derivative of g with respect to y. Okay, I'm going to continue this problem here. So then we're left with the fact that the derivative of that function g with respect to y equals to 3z. So then we have to integrate it again. Okay, so I want to solve for that g. So I'm going to put dg equals to 3z times dy. And to solve for it, I need to integrate it. So if I integrate this, we're going to be left with the fact that g of yz equals, what is the integration of 3z with respect to y? 3yz plus some constant. Now, that doesn't necessarily need to be a constant. Since we're evaluating this in terms of y, then it could be that we end up with a function of z. Or if it's not a function of z, if it doesn't depend on z, it could be that it is a constant. So it could be one or the other. Okay, so that's what we're going to determine. So this is how we're going to determine if this is a function of z or if it's not a function of z. We're going to use our last condition. Okay, so but before we do that, I'm going to substitute all of this into the original function. So we have the original function to be this one. So f of x, y, and z equals to 3xy plus 4xz plus, and then the function g of yz, which is right here, 3yz plus some function, possible function h of z, or maybe a constant. We don't know. Okay. So now let's use the last condition. The last condition requires us to find the derivative of the potential function with respect to z. Okay. So I'm going to get the derivative of this function with respect to z now. The derivative of 3xy with respect to z is 0. The derivative of 4xz with respect to z is 4x. The derivative of 3yz with respect to z is 3y. And the derivative of h with respect to z would be dh over dz. And what do we know here? We know that the derivative of f with respect to z is equal to 4x plus 3y. Okay, 4x plus 3y. So 4x plus 3y equals 4x plus 3y plus the derivative of h with respect to z. So that's going to give us a 0, as you can see. So then dh with respect to z is going to be equal to 0. Okay? In other words, this function does not depend on z. So that means that this is our final answer. Ready? Our potential function, okay, is going to be this. Moving from the blue one, 3xy plus 4xz plus 3yz. Since this function does not depend on z right here, this last function h, then it would just be plus some constant c. And this is the potential function. So what does it mean by potential function? It means that if we get the gradient of this function, the gradient of this function is basically the same as this right here that we obtained, as we're given as this field. Okay, let's verify that. What is the derivative of this with respect to x? 3y, and this one with respect to x would be 4z. 3y plus 4z. So we go up 3y plus 4zi. Okay. Now, what is the derivative of this potential function with respect to y? It would be 3x, and right here with respect to y would be 3z. 3x plus 3z. That's what we have as the j component. Okay. And then what is the derivative of this potential function with respect to z? Right here would be 4x, and right here would be 3y. So it would be 4x plus 3y. If we go up, that is the k component of this field. So anytime a field is conservative, then we should be able to find a potential function so that that potential function equals to the gradient of some, that is equal to some gradient of some potential function. Okay, that is how we actually find that possible potential function, by integrating and making sure that we use each one of these conditions one at a time. Let's do another potential function. Now we're going to find the potential function for this field. But before we do that, we're going to verify that it actually that is actually a conservative field. That's what we need to verify first. Okay. Let's do the verification for a conservative field to see if it is that we can find a potential function for it. So the derivative of the k component right here, with respect to, what is it, with respect to y. So this is just a constant, right now. So maybe, you know what, I can distribute that first. That will be easier if I do that. F equals to 5e to the 3y plus 4zi plus 15x times e to the 3y plus 4zj plus 20x times e to the 3y plus 4zk. So then we're going to start by getting the derivative of the last component with respect to y. So the derivative with respect to y would be 3 times 20x, which is 60x, times e to the 3y plus 4z. And according to this, it has to be the same as the derivative of the j component, which is the middle one, with respect to z. The derivative of this with respect to z would be 4 times 15, which is 60x times e raised to the 3y plus 4z. And we can see that they are the same. Let's check on the next one. The derivative of the first component with respect to z, it would be 4 times 5, which is 20, e to the 3y plus 4z. And now we're going to get the derivative of the last component with respect to x. So with respect to x, it would be the derivative of 20x would just be 20, right? So that will give me also 20 e to the 3y plus 4z. They are the same. Now check on the last one. The derivative of the middle component with respect to x, the derivative of 15x will be 15. So it's 15 times e to the 3y plus 4z. and the derivative of the first component with respect to y, the derivative of 3y would be 3 times 5. It would be 15e to the 3y plus 4z. And we can clearly see that it satisfies the condition of a conservative field. So we can say that F is a conservative field. Therefore, we can say that F is equal to the gradient of some potential function F. Okay, so that's what we're going to work on next. Since F is equal to the gradient of some potential function F, then this component of the field represents the derivative with respect to x of some potential function. This represents the derivative with respect to y of some potential function, and this component represents the derivative with respect to z of some potential function. That's what we would set next. So the derivative of some potential function with respect to x equals to 5e to the 3y plus 4z. Then the derivative of some potential function with respect to y is equal to 15x times e raised to the 3y plus 4z. And last but not least is that the derivative of some potential function f with respect to z equals to 20x times e to the 3y plus 4z. And now we're going to work this out. Okay, we're going to start by getting the integration of this. So the derivative of some potential function equals to 5 times e to the 3y plus 4z times dx. So we're going to integrate it. Let me erase this. So we're going to integrate it with respect to x. Okay, so the integration of this constant with respect to x is just 5x times e to the y to the 3y plus 4z. And that will give us a potential function f in terms of x, y, and z equals to 5x times e raised to the 3y plus 4z. And then plus, now we could have a constant, or since we're evaluating it with respect to x, we could end up with a function in terms of y and z instead of a constant. So to determine if it's going to be a function in terms of y, a function in terms of z, or a function in terms of y and z, or just a constant, we need to use the second and the third conditions. So, second condition. We are required to get the derivative with respect to y now. The derivative of this potential function with respect to y to use this condition now. So that's what the next step would be. So the derivative of this function with respect to y is going to be the derivative of 3y to the 4z plus 4z would be 3 times 5x would be 15x e to the 3y plus 4z plus the derivative of this function g with respect to y. But we know that this is equal to that, so we're going to replace it in here. So that is equal to 15x times e to the 3y plus 4z equals to 15x times e to the 3y plus 4z plus the derivative of some function g with respect to y. You see that this function does not depend on y because we got that 0, the derivative of g with respect to y is equal to 0. Okay? So that means that this could possibly be a function with respect to z. Could be. We're not saying that it will be, but it could be. So then that potential function could be this. 5x times e to the 3y plus 4z plus some function h with respect to z. So now we're going to use the last condition. Get the derivative of this function with respect to z and see if it depends on z. The derivative of this with respect to z would be 4 times 5x, which is 20x times e raised to the 3y plus 4z, plus the derivative of this function h with respect to z. So then I'm going to substitute this. We already know this value, so I'm going to plug it in here. So then we have that 20x times e to the 3y plus 4z equals to 20x times e to the 3y plus 4z plus the derivative of some function h with respect to z. So that tells us that also this function does not depend on z, because we got a 0. Okay? So then, what can we say at last about our potential function? That this is not a function with respect to y, or this is not a function with respect to z, but that is just a constant. So the potential function will then be f of x, y, z equals to 5x times e raised to the 3y plus 4z plus some constant c. This is the potential function. We can verify the result by getting the derivative with respect to x, the derivative with respect to y, and the derivative with respect to z, and check on the gradient field that we created right here and see if it gives us that. So if we get the derivative with respect to x right here, it would be 5 times e to the 3y plus 4z. That's what we have right here. If we get the derivative with respect to y, it would be 3 times 5x, which is 15x, times e raised to the 3y plus 4z, which is the j component. If we get the derivative with respect to z, it would be 4 times 5x, which is 20x, times e raised to the 3y plus 4z, k. And you see that that potential function that we obtained gives us this gradient field. Next. Now for this one, we would basically do the exact same thing, okay, for the potential function. All right. So I'm going to skip this part and I'm going to go to something else. Okay. The next thing we're going to work on, okay, exactness. Any expression m dx plus n dy plus p dz is a differential form. Then a differential form is going to be exact if m dx plus n dy plus p dz equals to the derivative of f with respect to x dx plus the derivative of some potential function f with respect to y dy plus the derivative of some potential function with respect to z dz. You see that that's going to give us basically just the derivative of the potential function. So that's what it means by exact, that it will exactly give us the derivative of the potential function. Okay? So what does that mean? Exactness means conservative field. So if a field is conservative, that means that the differential is going to be, this differential right here is going to be exact. If this field, if some field mi plus nj plus pk is conservative, then its differential m times the derivative of x plus n times the derivative of y plus p times the derivative of z is going to be exact. Okay. And let me see if I can find one definition that I lost. Okay, so I think we're fine. Alright, so let's continue with this. Show that the differential form in the integral is exact, then evaluate the integral. 6x to the 5th y dx plus x to the 6th minus z to the 4th dy minus 4yz cubed dz. We want to get the integral from 0, 0, 0 to 1, 2, 3. Okay? So what we need to determine, first of all, right here it would be really hard to evaluate the integral, especially because of this triple point, and because this is dx, this is dy, this is dz. So it will be like a long process to do the integral the way it is written. So we're going to use the following definition. First of all, we're going to determine if this is exact. Okay? To determine if it's exact, what we need to do is determine if this field f equals 6x to the 5th yi plus x to the 6th minus z to the 4th j plus negative 4yz cubed, okay, it's conservative. Okay, remember that this is m, this is n, and this is p. So we're going to get the derivative of the k component with respect to y. What is the derivative of this component with respect to y? Negative 4 z to the 3rd. The derivative of the j component with respect to z would be negative 4 times z to the 3rd. And you can see that these two are the same. Now, get the derivative of the first component with respect to z. The derivative of this with respect to z, since there is no z, it is 0. The derivative of the last component with respect to x, since there is no x, it is also 0. So that is true. And last but not least, the derivative of the j component with respect to x is 6x to the 5th power. And the derivative of the I component with respect to y would be 6x to the 5th power as well. So we can see that this field, since all the components of the conservative field are met, then we can say that f is conservative, which means that what's called the differential 6x to the 5th y dx plus x to the 6th minus z to the 4th dy minus 4yz cubed dz is exact. And by exact means that if we get the potential function of this field right here, we can evaluate the potential function directly to these limits instead of having to integrate this. Okay? Alright, so let's get the potential function. Okay? Remember, by f is conservative, we mean that f equals, the field f is equal to the gradient of some potential function f. Meaning that this component represents the derivative of some potential function with respect to x. This component represents the derivative of some potential function with respect to y. And this component represents the derivative of some potential function with respect to z. So let's integrate this one. The derivative of some potential function equals to 6x to the fifth y times dx. So we need to integrate it, and the first integration will be with respect to x. So the integration of this with respect to x will be, well, first of all, f of x, y, z equals the integration of 6x to the fifth with respect to x will be x to the sixth power y, plus it could be that it is plus some constant or some function g. Since we're evaluating it with respect to x, it could be that this function is a function with respect to y and z. Okay. Now, to determine if it depends on y or z or both or just one or none, we have to use the second condition. First, we need to get the derivative with respect to y of this field. The derivative of this field with respect to y equals derivative of x to the 6y with respect to y would be x to the 6th, plus the derivative of g with respect to y would be dg d over dy. And we know that this equals this, so we can substitute it back into the derivative of f with respect to y there, and we are left with x to the 6th minus z to the 4th equals x to the 6th plus the derivative of some g with respect to y, some function g with respect to y. So then we can say that the derivative of g with respect to y equals negative z to the 4th power. So now to get that function g back, I need to integrate again. But now that integration, when I move the dy over, is going to be with respect to y. So I'm going to integrate this with respect to y, and the integration is going to give us g of yz equals, with respect to y, is negative yz to the 4th power plus possibly some function h with respect to z, or maybe a constant. We never know. So before we continue, I'm going to replace that into my original function. So my function of x, y, z, my potential function, equals x to the 6th y plus, and g of yz is this. I should have put minus yz to the 4th plus some function h of z, or maybe a constant. Could be a constant. How do we finalize this? Now we're going to use the third condition. To find this function, if it's a function of z or a constant, use the third condition. Get the derivative of this potential function with respect to z. The derivative of this with respect to z is 0. The derivative of this with respect to z would be negative 4yz to the 3rd, and the derivative of h with respect to z would be dh over dz. And you see that we know that df over dz equals to this, so we're going to replace it in here. So we're left at negative 4yz to the 3rd equals to negative 4yz to the 3rd plus dh over dz, which means that dh with respect to z equals to 0. So this potential function does not depend, the h of z does not depend on z. So that means that it is just a constant c. Okay? So then we can write the potential function. This is our last step in the process. So the potential function is going to be f of x, y, z equals to x to the 6y minus yz to the 4th plus some constant c. And this is the potential function. You can verify that this is a potential function for that gradient field by just getting the gradient of this function. And the gradient of this function, just like I showed you before, it has to give you this gradient field given on this part. Next. Okay. Oh, I'm not done. I forgot one more thing. So this question, we needed to get the potential function, but for one reason. We wanted to evaluate this integral. Now that I found the potential function, I can apply this definition that we had in one of the first slides. Right here. Let C be a smooth curve joining the point A to the point B, parameterized by r sub t. Let f be a differentiable function with a continuous gradient vector. F equals to the gradient field, some gradient field equals to the gradient of some potential function f on the domain of D containing C. Then the line integral is the same as the potential function evaluated at B minus the potential function evaluated at A. Okay, so that's what we're going to do right here. Where are we? Here. You see that we're going to evaluate it at 1 to 3 minus, this is your f of B, this is your f of A. So we're going to evaluate it at 1 to 3 and then at 0, 0, 0. So then we're going to say that the integral from 0, 0, 0 to 1, 2, 3 of 6x to the 5th y dx plus x to the 6th minus z to the 4th dy minus 4yz cubed dz will just be the same as the potential function evaluated at the 1 to 3, which is going to be f of 1, 2, 3 minus f of 0, 0, 0 according to the definition, which is, when I put a 1 to 3, we're going to get 1 to the 6th power times 2 minus 2 times 3 to the 4th power plus some constant c minus, evaluate them at 0. 0 to the 6th times 0 minus 0 times 0 to the 4th plus some constant c. Okay. Now evaluate this. This will be 2 minus 81 times 2 would be 162 plus c minus 0 minus 0 plus c. That's going to give us negative 160 plus c minus c, which is negative 160. So if we were to evaluate this integral directly, the way it is with respect to x, with respect to y, with respect to z, evaluated from f of A to f of b, then it will give us exactly the same as this result as evaluating it directly to the potential function. Next. We're going to do another one like that. Show that the differential form in the integral is exact. To show that it is exact, we need to prove that this field is conservative. That's what we need to do. So let's do the same thing. First, we need a field. We're going to get the field right here. Sine of y, cosine of x, I, this is the m component, plus cosine of y, sine of x, j, this is the n component or the j component, and then plus 6 k. This is the k component. That's your p. So we need to get the derivative of the last component with respect to y. Since there's no y, it's 0. And the derivative of the middle component with respect to z. Since there's no z, then it is also 0. So that is true. The derivative of the first component with respect to z. Since there's no z, it is 0. The derivative of the last component with respect to x. Since there is no x, it is also 0. That's true. The derivative of the middle component with respect to x, it would be cosine of x times cosine of y. And the derivative of the first component with respect to y, the derivative of sine of y is cosine of y times cosine of x. And you can see that is actually the same. So all the three conditions were met. So that means that f is conservative. And since f is conservative, that implies that the differential sine of y cosine of x dx plus cosine of y sine of x dy plus 6 dz is exact. And by exact, we mean that we can find a potential function for this gradient field and evaluate it directly to these limits. And it's going to be the same thing as doing this integration. Okay. So let's go ahead and find the potential function. So again, by conservative, we mean that the function f, this gradient field f, is equal to the gradient of some potential function. Okay, so that means by the gradient of some potential function will mean that this component is represented by the derivative of some potential function with respect to x. This component represents the derivative of some potential function with respect to y. And this component represents the derivative of some potential function with respect to z. Okay. So now we're going to do the integration. The derivative of some potential function equals to sine of y cosine of x dx. So we're going to integrate it with respect to x right here. So the integral of sine of y cosine of x with respect to x, the integration of cosine of x will be sine of x. So then we're going to get a potential function in terms of x, y, z equals sine of y times sine of x, plus, since we're evaluating it in terms of x, then we're going to have possibly some function g in terms of y and z. It could be that it is a function in terms of y. Could be that it is a function in terms of z. It could be that it is a function in terms of y and z, or it could be that it is just a constant. That's what we're going to determine by using again the other two conditions. Okay? To use the second condition, what we need to do is get the derivative of this potential function now with respect to y. The derivative of sine of y would be cosine of y times the sine of x, of course, plus the derivative of g with respect to y. And we already know that the derivative of the potential function with respect to y equals to that, so we're going to substitute it. So we get, give me 1 second, cosine of y sine of x equals cosine of y sine of x plus the derivative of g with respect to y. And you see that we're going to get that the derivative of g with respect to y is going to be equal to 0. So that means that this function does not depend on y. It could be that it depends on z, That's what we're going to determine next with the last condition. So I'm going to change it. And instead of saying plus some function with respect, I'm just going to call it differently. I'm going to call it h now. Instead of some function with respect to y and z, it could be that it is a function with respect to z. Or maybe just a constant. So, to make the use of the last condition, we need to find the derivative of this potential function with respect to z. The derivative of this is going to be a constant with respect to z, so it's going to be 0. And this is dh with respect to z. So then dh with respect to z is going to equal to df with respect to z, which is equal to 6. So dh with respect to z is just going to be 6. Okay? But now we need to solve for that function h. How? By integrating this. So I'm going to solve for dh. dh equals to 6 dz. And we're going to integrate it for one more time. The integration of this with respect to z would be h of z equals to 6z plus, now since we already integrated it with respect to all three, then it's going to be plus some constant c. So let's write our potential function. The potential function is going to be f of x yz equals to, let's write the beginning, sine of y sine of x plus h of z, which is 6z plus some constant c. This is our potential function. Now we're gonna, since we already know the potential function that gives us the gradient field given right here, now we should be able to directly, since this integral is exact, this differential is exact, we already found out by finding that f is conservative. Now we can evaluate this integral directly through these limits by the f of b minus f of a using the potential function found. Okay, so we want to go from 1, 0, 0 to 1, 0, 5. Okay, f of 1, 0, 0. Oh, I have to do f of b first. 1, 0, 5 minus f of 1, 0, 0. Is that what it is? Yes. That is equal to sine of 0 sine of 1 plus 6 times 5 minus, I forgot one thing, if you can see what I forgot, plus c minus, now evaluated at 1, 0, 0, so sine of 0 sine of 1 plus 6 times 0 plus c. And this is going to give us 0 plus 30 plus c minus 0 minus 0 minus c, which is going to be equal to 30. So if we were to evaluate this integral directly, since this differential is exact, then that should give us the same value as 30, which is evaluating it directly through the potential function of this gradient field. Next. Alright, so we're going to do probably a few more on potential functions. Okay, so show that the differential form below is exact, then evaluate the integral. Okay, let's test it out to see if it is exact. We need a potential function, we need what's called a vector field first from this differential. So that's going to be 27 x squared I plus 2z squared over y j plus 4z ln of y k. This is your m, n, and p components of this field. So the derivative of the last component with respect to y would be 4z times 1 over y, which is 4z over y. Okay. Now the derivative of the middle component with respect to z would be 2 times 2z, which is 4z over y. So it gave us exactly the same thing. So that one, so far, the conditions of a conservative field are met. So the next one, the derivative of the first component with respect to z, since there is no z, it is 0. And the derivative of the last component with respect to x, since there is no x, it is also 0. Last but not least, the derivative of the middle component with respect to x, since there is no x, is 0. And the derivative of the first component with respect to y, since there is no y, it is also 0. So the three conditions for the conservative field are met. So we're going to say f is conservative. And by conservative, we mean that the differential 27x squared dx plus 2z squared over y dy plus 4z ln of y dz is exact. And by exact, again, we mean that I can find a potential function of this field and evaluate it directly to these limits instead of having to do this integration. Okay. So let's find the potential function. By f being conservative, we mean that f, this gradient field, equals to the gradient of some potential function f. And by potential function, we mean that this component represents the derivative with respect to x of some potential function f. This component represents the derivative with respect of some potential function with respect to y. And this component represents the derivative of some potential function with respect to z. And now we're going to start integrating to find that such potential function with those that meet those conditions. So we're going to get df equals to 27x squared dx. So we're going to get the first integration with respect to x. So when I integrate it with respect to x, we get that some function in terms of x, y, and z equals the integration with respect to x is 27x cubed divided by 3, which is 9x cubed, plus some function g in terms of y and z. Maybe in terms of both, maybe in terms of y, maybe in terms of z, or maybe just a constant. That's what we're going to use the other two conditions for. Okay? To determine if it's a function of y, we're going to use the second condition. Get the derivative with respect to y of this gradient field, of this, potential function that we are finding. The derivative of the potential function with respect to y equals, since there is no y, this is going to be 0. So that's just going to give you equals to the derivative of g with respect to y. So, but we know that this is equal to this right here, so we're going to substitute it. We're going to evaluate it right here. So then we're going to get that 2z squared over y equals to dg with respect to y. Then if I solve for dg, we're going to have the derivative of g equals to 2z squared over y dy. And we're going to integrate it. Then g of yz equals the integration of dy over y is L natural log of y. So that will give me 2z squared times natural log of y plus possibly some function h with respect to z, or maybe a constant. We don't know yet. Okay? So before we do that, let's substitute this back into the function g right here. Okay? So all of this, we're going to plug it back in here. So we get that the function of x, y, and z is equal to 9x cubed plus 2z squared natural log of y plus some function, possibly constant, okay, of z. So to find out if it is a function of z, then we need to use the third condition. We need to get the derivative of this potential function with respect to z to use this third condition. So the derivative of this function with respect to z equals, this one is going to be 0. The derivative of this with respect to z would be 4z natural log of y plus dh with respect to z. The derivative of this function h with respect to z. And you see that we can evaluate this. df over dz equals to 4z natural log of y, so we can substitute it here. And we end up with the fact that dh over dz is equal to 0. So that means that this potential function does not depend on z, meaning that this is only going to be some constant c at last. So what is our potential function? Let's put it here. F of x, y, z equals 9x cubed plus 2z squared natural log of y plus some constant c. Okay, so this is what we're going to use. This is our potential function, and since the differential on the top is exact, that means that we can evaluate the limits directly into this potential function, and that will be the same thing as the integral from that f of a to f of b. Okay, let's evaluate it now. Okay, so we want to go from 913 to 934. F of 934 minus f of 913. That's what we want to find. Okay, which is going to be 9 times 9 cubed plus 2 times 4 squared natural log of 3 plus some constant c minus 9 times 9 cubed plus 2 times 3 squared times natural log of 1 plus some constant c. Let's evaluate it. So let's see, let's use a calculator for this. Let's check it out. So 9 to the third power is 729 times 9, which is 6,561 plus this is 16 times 2, which is 32 natural log of 3 plus some constant c minus this is going to be the same thing, 6,561 plus 9 times 2 is going to be 18 natural log of 1, but natural log of 1 is going to be 0 plus some constant c. So we end up with 6,561 plus 32 ln of 3 plus c minus 6,561 minus 0 minus c. So you see that this is going to cancel out and this is going to cancel out. So we are left with 32 ln of 3. So if we were to evaluate the integral directly, like integrated directly the way it is right here, it should give us the same value as just evaluating it directly to its potential function of the gradient field given. Next. Okay, let's find a potential function for this one. So it says that although it is not defined on all space, the field associated with this line integral below is simply connected. So what it's saying basically that this is not defined over all values in space, because it is of course it has values for which it is undefined. Okay, but if it was to be sketched, the graph will be simply connected. Simply connected means not overlapping, and it will be connected like this, simply connected, if it was to be sketched. Okay, and the component test can be used to show that it is conservative. So now we're gonna show that it is conservative, and then so that we can determine that it is exact. Okay, and then we can find a potential function for that. So first of all, let's find the field, okay, gradient field. So that would be 1 over y I plus 1 over z minus x over y squared j plus negative y over z squared k. This is m, n, and p. So if I get the derivative of the p component with respect to y, the derivative with respect to y is negative 1 over z squared. The derivative of the middle component with respect to z, so that would be, this is the same thing as z to the negative 2 power, right? So when I get the derivative, it will be negative 2, z to the negative 1 power, I'm sorry. So when I get the derivative, it will be negative 1 times z to the negative 2, which is the same as negative 1 over z squared. So which gives us the same thing. The derivative of the first component with respect to z, since there is no z, it is 0. The derivative of the last component with respect to x, since there is no x, is also 0. You see? The derivative of the middle component with respect to x, this is a constant, so that's 0. The derivative of this one with respect to x is negative 1 over y squared. And the derivative of the first component with respect to y, so this is y to the negative 1 power. When I get the derivative, it would be negative 1 y to the negative 2 power, which is the same thing as negative 1 over y squared. And you see that the tests for a conservative field are all met. So that means that f is conservative, which means that 1 over y dx plus 1 over z minus x over y squared dy minus y over z squared dz is exact. And by exact means that I can find a potential function for this field and evaluate it directly to these limits, and that will be the same thing as this integral. Okay, and by the function, the field being conservative means that that is equal to the gradient of some potential function f. And by the gradient of some potential function f, that means that this component is the derivative of some potential function with respect to x. This component is the derivative of some potential function with respect to y, and this component is the derivative of some potential function with respect to z. So we're going to say that the derivative of some potential function with respect to x equals to 1 over y. The derivative of some potential function with respect to y equals to 1 over z minus x over y squared. And the derivative of some potential function with respect to z equals to negative y over z squared. Let's integrate the first one to start finding the potential function f. So the derivative of f equals to d, well, I'm going to put it as 1 over y dx. And the integration of 1 over y dx with respect to x, it would just be x over y, or 1 over y times x, which is the same thing as x over y. Okay, so we're going to get that the function, the potential function in terms of x, y, and z equals to x over y plus, since we're evaluating it at for the values of x, then we could have a function g in terms of y and z, maybe a function in terms of y, maybe a function in terms of z, or maybe a constant value only. So we're going to use the other two conditions to determine what it is. Okay. Second condition. Now we need to use this condition, we need to find the derivative of the potential function with respect to y. So the derivative of this potential function with respect to y equals this, the derivative with respect to y would be negative x over y squared plus dg with respect to y. But we already know that the derivative of f with respect to y equals to this, so we're going to evaluate it here. Use that condition. So we get that 1 over z minus x over y squared equals to negative x over y squared plus dg with respect to y. And so we can say that dg with respect to y equals to 1 over z. We still need to find that function g. So to find it, we need to integrate again. Okay? So we say that dg equals 1 over z times dy. And we're going to integrate this function. Okay? So then the integral will be g of y and z equals the integration of 1 over z with respect to y would be 1 over z times y, or y over z, plus possibly some function in terms of z or some constant. We don't know yet. Okay? To continue, what we're going to do is we're going to replace the value of g of yz, which is this, here. Okay? So f, the potential function f of x, y, z equals to x over y plus y over z plus some function in terms of z or some constant. We don't know yet. Okay? How do we determine if this is a function of z or a constant? We're going to use our third and last condition. The last condition requires us to get the derivative of this potential function with respect to z. So the derivative of this potential function with respect to z equals, since this doesn't have any z, so that's 0, the derivative of y over z with respect to z would be negative y over z squared plus the derivative of h with respect to z. And we know that this is equal to that. So we're going to substitute it. The derivative of the potential function with respect to z equals to negative y over z squared equals negative y over z squared plus dh over dz. So that means that dh over dz equals to 0. Right? So this function h is not a function of z, meaning that it will be just a constant value. So we're going to write the potential function. potential function would be f of x, y, z equals to x over y. I'm following this right here, plus y over z, and instead of a function of z, it would be some constant c. Okay, so since the integral is exact, we can evaluate it directly to its limits to this potential function. That's what we're going to do, using the original limits from f of 244 minus f of 132. Those are the two limits. F of 244 minus f of 132. Evaluate the first limits. So that would be x, which is 2, over y, which is 4, plus y, which is 4, over z, which is 4, plus the constant c, minus, evaluate these limits, x, which is 1, over y, which is 3, plus y, which is 3, over z, which is 2, plus some constant c. So that's going to equal to 1/2 plus 1 plus c minus 1/3 minus 3/2 minus c. The c's will cancel, so we just have to combine those fractions. 1/2 minus 3/2 is negative 2/2, right? Negative 2/2, which is negative 1, minus 1/3. That's going to be negative 4/3. So if I were to evaluate that integral directly, it should give me the same as this value of the potential function by evaluating the potential function towards those limits. Okay. We're going to do one last problem, and I guess it's going to be this last one, and that should be enough. We're going to let f be the gradient of that function, x to the third y squared. So first of all, before we start, let's get the gradient, okay? F is going to be the gradient of this function, meaning the derivative with respect to x, which is 3x squared y squared, okay, I, plus the derivative with respect to y, which is going to be 2x cubed y j. Okay, so, and we want c to be the path in the xy plane from negative 5, 5 to 5, 5. That consists of the line segments from negative 5, 5 to 0, 0, followed by the line segment from 0, 0 to 5, 5. Okay, so we're going to evaluate this integral in two ways. Number one, find the parametrizations for the segments that make up C and evaluate the integral. Now, right here, you can see, you would be able to find out that this field is conservative. Okay? Now, you should be able to determine that. If you're able to determine that this field is conservative, then that means that you should be able to evaluate it. Okay? You should be able to evaluate it directly to its potential function. This is a potential function that gives me this gradient. Okay? So check it out so that you can see that it is true. What is the derivative of p? You see that there is no k, right? What does it mean? 0k, right? What is the derivative of this value, of this k value, p, with respect to y? Well, it's 0. What is the derivative of the middle one with respect to z? Since there's no z, it is also 0. See? What is the derivative of the first component with respect to z? Since there is no z, it is 0. what is the derivative of the last component with respect to x? It is also 0 because it's already a 0. And last, what is the derivative of the middle component with respect to x? 3 times 2, which is 6x squared y. And what is the derivative of the first component with respect to y? 2 times 3, which is 6x squared y. And you see that this field is conservative. So, since this is a potential function of this field, then one thing that we can do, and that's what they want you to do on letter B, we can evaluate this integral directly from negative, from instead of going from -5 to 5, instead of going from -5, 5 to 0, 0, and then from 0, 0 to 5, 5, we can just evaluate it directly to this potential function, okay, from -5, 5 to 5, 5 directly, okay, because this integral is exact. This proves that the integral is exact, okay, the differential, okay. So then what we're going to do, letter B, since it is exact, we can automatically just evaluate the integral directly. I'm going to start with letter B, okay. So I'm going to go and evaluate it as f of 5, 5, which is f of B, minus f of A, which is f of -5, 5. This is f of B, and this is f of A. This is A and this is B, right? From A to B. So that's going to be, the potential function is this one, x cubed y squared. So then I can put it as 5 cubed, 5 squared, minus -5 cubed, 5 squared. That is going to be, I don't know, 125 times 25, which is 3,125. This is -125 times 25, so minus -3,125, which is 6,250. That's the value of the integral. So you will see that now we're going to do it in a different way. This is the proof that it actually works. Okay? So now by evaluating it directly to a potential function, that gives you this that gives you this gradient field. Okay? So that was the potential function that gives me this field, right? So now, and that only happens if the integral is exact. In other words, if the field is conservative. Okay? Since this is conservative, now we can find the integral directly like this. But now we're going to do this integral in a different way, so you see that it is actually true. Okay? And by conservative, remember that the inline integral will be equal through any path that we take. It will be the same values, right? So if I just do the integral from -5, 5 to 0, 0, and then add it to the integral from 0, 0 to 5, 5, that's the same thing as going from -5, 5 to 5, 5. But now we need to find two parametrizations to go from one point to the other one, and then for the other ones as well. Okay, that's part A. Let's find a parametrization to go from -5, 5 to 0, 0. Okay, the parametrization could be -5 plus, since it is increasing by 5, then we're going to say plus 5t. And we can say from t equals to 0 to t equals to 1. Because when t is equal to 0, it goes from -5, and when t is equal to 1, it goes to 0. Right? So that would be I. Plus, now this one is decreasing by 5, so it would be 5 minus 5t, j. And we can directly say that this goes from t is equal to 0 to t is equal to 1. That would be C1. Okay? Let me just put it like that. C1. Okay? Let's find also C2. So C2 is going to go from 0, 0 to the last point, 5, 5. Yeah. So C2. So what would be the second parameterization? It is increasing by 5, so it would be 0 plus 5t, which is just 5ti. This one is going from 0 to 5, so it starts at 0, so 0 plus 5t, which is just the same thing as 5tj. And it goes from t equals to 0 to t equals to 1. Okay, so the sum of the two line integrals will give me the same thing. Okay. So we already got the gradient field, which is this one. Remember that what we need to do now, we need to evaluate this gradient field to each one of these parametrizations. Okay, where x is going to be this and y is going to be this, and for the second one, x is going to be this and y is going to be the 5t. Okay, so let's do the first parametrization. Okay, I just want to point something out, that these two are basically the same thing, because it's going to make it easy. But this is just the same as negative 5, negative times negative 5 plus t, right? Negative 5 plus 5t, I'm sorry. So you basically, this is the same thing as this, with the exception that this one is negative, right? Or this one is negative, whichever way. Okay? So I'm saying that because now we're going to evaluate the function. We're going to do the first parameterization for C1. Okay? We're going to find f or of r's of t. Okay? So remember that f is equal to 3x squared y squared, I. So 3, and instead of x would be negative 5 plus 5t squared times y squared. I'm going to use the bottom one for one reason. You will see. Negative 5 plus 5t squared. Okay, this is I. Plus, now evaluate the j. The j says 2x cubed y. So it would be 2, and instead of x, we're going to put this, negative 5 plus 5t cubed times y, which is negative, times negative 5 plus 5t. J. Okay. So let's do the evaluation. Do you see the reason why I put it like this? Because negative, when I square it, that's going to become a positive, right? So, and this square times this same thing square would just be the same as negative 5 plus 5t to the 4th power. And that negative became positive when I squared it. See? Right here, the same thing. Negative times 2 would be negative 2. And right here, we're going to have negative 5 plus 5t to the 3rd power times negative 5 plus 5t would be negative 5 plus 5t to the 4th power. And then remember what we have to do. The next thing is that we need to get the derivative of this position. Okay? The derivative of that position is equal to, the derivative of this x would be 5i. The derivative of this y would be negative 5j. So it will be 5i minus 5j. Then to get the work integral or the line integral, we need to get the dot product. Get the dot product of these two. 5 times 3 would be 15 times negative 5 plus 5t to the 4th power. Negative 5 times negative 2 is positive 10 times negative 5 plus 5t to the 4th power. And since these two are the same, I can combine like terms. 15 plus 10, that would be 25 times negative 5 plus 5t to the fourth power. So then the integral will be, the first integral goes from, what are the limits? From 0 to 1, you see? Of this, 25, I can put the 25 on the outside, and that's what I'm going to do. 25 times negative 5 plus 5t to the fourth power dt. This one, you're going to do a u substitution. This is like u to the power of n. But the derivative of this is going to be a 5. So I need to put a 5 here, and that's your du, right? But I need to do a 1/5, or divide by 5 right here on the outside, right? So then this is u to the power of 4 du, which the integral gives me negative 5, I forgot the on the outside, 25 divided by 5, which is 5, times negative 5 plus 5t to the fifth power divided by 5 from 0 to 1. See what happens? So then you get evaluated at 1, negative 5 plus 5, it's going to be 0, minus evaluated at 0, so that will give me negative 5 to the fifth power. So let's see, which is negative 3,125. So that would give me, yeah, negative 3,125. Wait, there's a problem. It was minus f of b, minus f of a. So it was minus, and that gave me a negative 3,125, so that's going to be a plus. Okay, yeah, that was my mistake. Good. So now we're going to get the integral along path number 2, which is from 0, 0 to 5, 5. We found the parametrization. Okay, now we need to write the function in terms of that parametrization, the field in terms of that parametrization, where x is equal to 5t and y is equal to 5t. So instead of 3x squared y squared, we're going to put 3x, which is 5t squared, times y, which is 5t squared, plus, and on the j would be 2x cubed y, but instead of 2x cubed y would be 2 times 5t cubed times y, which is 5t, and that is j. This gives us 5t to the fourth power, which is 625 times 3 in the front, which is 1,875 t to the fourth power. Plus 5t to the third times 5t would be 5t to the fourth power, which is 625t to the fourth times 2, 1,250 t to the fourth power j. Now we need to get the derivative of my parametrization function, my parametrization vector. The derivative would be 5i plus 5j. And then we're going to get the dot product. The dot product of the function in terms of the parametrization with the derivative of the parametrization. So 1,875t to the fourth times 5, that's what we need to multiply. 1,875 times 5, it would be 9,375 t to the fourth power, plus 1,250 t to the fourth times 5, let's see, that would be 6,250 t to the fourth power. When I combine them, that would be equal to 15,625 t to the fourth power. So now we're going to do the integral. The integral from 0 to 1 of 15,625 t to the 4th dt. So it would be 15,625 t to the 5th divided by 5 from 0 to 1. When I divide that by 5, it gives us 3,125 t to the 5th from 0 to 1, which is going to be 3,125. So how do I get the total integral from the first point, which is from negative 5, 5 to 0, 0, connected to from 0, 0, then to 5, 5. We just add the two values that we found, which is this one and this one. So that will give us a total. 3,125 plus 3,125. That is equal to 6,250. And that is the same as just evaluating the integral directly to the limits directly to the potential function of that gradient field. Okay, and this basically proves many things that I wanted to get away with in this section, so that you understood basically what the conservative field properties were and everything on its functions. Okay, so this will conclude section 15.3.